Alright guys, let's start vodcast 10.4. This should be the last vodcast for solutions, or at least the last major one. We might have a minor one with a couple other things that we left out. This vodcast is going to be on colligative properties, and if you're wondering what all this stuff on the side here, it is salt, and we'll see why in just a second why that's necessary. So, being at the time of the year, in the winter here in Tennessee, a lot of times we get some pretty icy roads, and of course, every time that happens, it's a real big deal, kind of because we're in the south, and so we're not as used to dealing with it as they are up north. But what that means for us is that anytime there's icy roads, they want to try to get rid of the ice on the roads. And of course, the way that they typically do that is what? Yeah, they're going to add salt to the road, or sometimes if you're listening to them, they'll say that they're adding a calcium solution, which is typically a calcium chloride solution, directly to the road. So what do they do that for? Okay, we think, okay, what happens there is that the salt melts the ice, and that is kind of what happened. But there's a good chemical reason, or really it's sort of a physical reason, but there's a good chemical reason for why salt added to an icy road is going to cause the ice to melt. Okay, and that's what we're going to talk about in this section of colligative properties. That's one of the ideas that we're going to be shooting for here. Okay, so what are colligative properties? Basically, colligative properties are you've got solutions, and the colligative properties of those solutions only depend, or not only, but mainly depend on the number of solute particles contained in the solution. Okay, now remember, what does that mean? Okay, so if we have an aqueous solution of sodium chloride, then the particles of sodium and the particles of chlorine are the solute particles that are in the solution. Okay, in other words, it's not the solvent particles, okay, which would be the water in this case, but it's the solute particles. Okay, to be able to do these calculations, and really even more than do the calculations, to be able to know what's going on in colligative properties, we have to know about something called the Van Hoff factor. The Van Hoff factor is the number of particles that any compound forms when it's in solution. The Van Hoff factor is usually labeled as a lowercase I. So when you see it in an equation and you see an I there, in chemistry that means number of particles. Now obviously if you're talking about math, it means square root of -1, but that's something entirely different. And plus that's sort of like that italic I anyway. And now that I've just thoroughly confused you. Anyway, the I here is the Van Hoff factor, which is the number of particles. Now, the way this works is that for a molecular compound, okay, any molecular compound always has one particle. Okay? In other words, its Van Hoff factor is always 1. I equals 1 for every molecular compound. Okay? And just to review real quick, how do I know if something's molecular? Remember, everything in it has to be a nonmetal. Carbon's nonmetal, hydrogen's nonmetal. Okay? Carbon dioxide, both nonmetals. Okay? Something like glucose, or sucrose rather, table sugar. Okay? That would, and I think I might have actually written that formula wrong. I think it's C12O11. But that is sucrose, so sugar that you would put into something, it has a Van Hoff factor of 1. Okay? Any molecular compound, I is always 1. Van Hoff factor is always 1. For ionic compounds, it gets a little bit more complicated. For any ionic compound, you basically have to, at least in your head, break it up into the number of particles that it breaks up into. So, sodium chloride becomes a sodium ion and a chlorine ion. Okay? Calcium chloride breaks up into a sodium. Yes, definitely. Calcium chloride breaks up into a sodium ion. No, not true. It breaks up into calcium, which has a 2+ charge, and it breaks up into chloride again, right? But how many chlorines do I have? I have 2. Okay? So what does that mean for the particles? Well, up here for sodium chloride, that means my I, my Van Hoff factor, equals 2 for sodium chloride, and my I equals 3 for calcium chloride. If we look down here for iron hydroxide, okay, or iron 3 hydroxide to be more appropriate, it breaks up into an iron, okay, and it breaks up into hydroxide. And how many hydroxides do we have? We have 3 of them. So what's my total number of particles? Okay, it's 4. Now, that's going to come into play a lot, because what this means is if colligative properties are things that are affected by how many particles it breaks up into, then I'm going to get a lot more colligative properties out of iron hydroxide than I am out of sugar or even out of other ionic compounds like salt and calcium chloride. Okay, why? Because it breaks up into more particles. So for every 1 molecule of this, I get 4 total particles. For every 1 molecule of sodium chloride, or 1 formula unit of sodium chloride, I get 2 particles. Okay, so that Van Hoff factor becomes pretty important. Now, it becomes especially important when we want to compare things that are equimolar. That seems like a really complicated word, but it actually means pretty much just what it sounds like. Equa means equal, okay, and molar means the concentration in molarity. Okay, remember capital M, that's molarity, moles per liter, okay? And so that basically means that if 2 things have the same molarity, they are what we call equimolar. So a 1 molar solution of sodium chloride is equimolar to a 1 molar solution of calcium chloride. Okay, so what that means is that if you remember the last slide, this breaks up into 2 particles, this breaks up into 3 particles, okay? So if we have equimolar solutions, then this one's going to have more colligative properties than this one. Why? More particles here, as long as it's the same number of moles, right, or the same molarity. Okay, so let's get into a little bit of what colligative properties actually are then, okay? The things that colligative properties affect, and the main thing that it affects everything else basically, is vapor pressure. So let's go back to the idea of vapor pressure that we talked about earlier in the year. So let's say that we've got a liquid, okay, these are water molecules, and we've got a flask and we've got some water molecules in it. And if you remember, these water molecules are all moving around. Whoops, hopefully the flask isn't moving around. The water molecules are all moving around kind of all over the place, right? That's what kinetic theory says. And kinetic theory says that if some of the particles have enough energy and they're close enough to the surface, that they're going to escape the liquid phase and go up and be in gas phase, okay? And the more energy it has, or the hotter it is, basically, the higher the temperature, the more of these water molecules that can escape into gas phase. And that's what vapor pressure is. Vapor pressure is the gas phase molecules colliding into the sides of the container. That's the vapor pressure, okay? So what colligative properties do is they are going to reduce the vapor pressure. And here's how they reduce the vapor pressure. If we start dissolving a sodium chloride, now remember when it dissolves, it breaks up into sodium ions and chloride ions. Okay, so we've got these things all over the place. What starts to happen, and this becomes relatively obvious pretty quickly, is once you start to add some of these particles in, they are going to actually sort of physically block some of these water molecules from being able to escape. There's just not room on the surface, even if they have enough energy, to be able to get out of there. Okay, so what that means is that it's going to lower the vapor pressure for the solution. Adding the sodium chloride is going to reduce the vapor pressure. Okay? So, knowing that, if we've got these 4 compounds, which one is going to have the lowest vapor pressure? Okay, and the key term here is we have to know that they are equimolar, which means we can basically assume that they're all 1 molar or 6 molar or whatever. It doesn't really matter. They all have the same molarity. So if that's the case, then what determines the vapor, which one has the lowest vapor pressure? Okay, and remember, higher colligative properties or more particles means lower vapor pressure. Okay, more particles. Okay, lower vapor pressure. Okay? So how many particles do each of these things form? Well, CO2 is a molecular compound, always has 1 particle, right? And we've done these other 3 before. We know that we have 2, 3, and 4 particles then. And if they're equimolar, in other words, the molarity isn't going to matter for us because they're all the same, then this one has more particles, and therefore iron hydroxide is going to have the lowest vapor pressure. Okay? Why? Because for every molecule of it, I would have a lot more particles in here blocking the molecules from being able to escape into gas phase. Okay, so I promised at the beginning that we would talk a little bit about why would we add salt to roads, and that all has to do with something called freezing point depression. The word depression means lowering, okay, or a low point, And so what this means is that colligative properties say that if we add particles into a solution, that we depress or we lower the freezing point. Okay, now how does that work? Well, in its normal state, okay, the liquids are going to form into a crystalline solid state here. If we add solute particles in, and that's what the little yellow pieces here are, they are actually, again, going to sort of physically block the crystalline structure from being able to form right away. And so you're going to need a little bit lower temperature to be able to then accomplish that actual freezing, okay? And so it works the same way as vapor pressure, that we can just look at a couple of compounds and tell which one is going to be more effective. So like if I said, okay, well, I've got a solution of glucose, this is sucrose, okay? And if I had some CO2, and then I had my good old salt, and just to mix things up a little bit, let's say that we've got some, let's say we're throwing some magnesium bromide in there. Pretty unlikely, but let's just say that that's what it is. Let's say they're all equal molar. And so which one is going to lower the freezing point the most? Well, again, it depends on Van Hoff factor if we don't work out the whole calculation, and we'll talk about that here in a second. So if they're all equal molar, then I've got one particle, two particles, and then magnesium is 1, and then 2 bromines gives me 3 particles, okay? So that means that magnesium bromide is going to have the lowest freezing point, okay? More particles, lower freezing point, all right? Now, that is sort of like a rough estimation for how that works, but we can actually do a calculation for that, okay? And this is the formula right here. It seems like it's really complicated, but it's not. If you read what each thing is, it's pretty easy to tell. Remember that anytime you see a delta, that means a change in. So what this means is the change in the freezing temperature. Okay, delta means change in. T is temperature. F here stands for freezing. So the change in the freezing point is equal to I, our Van Hoff factor, times little m. Remember, little m is molality. Okay, and remember from that section that molality is moles over kilograms of solvent. Okay? And then Kf is a constant that is related to the solvent. And here's what's tricky. Kf depends on the solvent, not on the solute. So in other words, the fact that in my example that we're about to work, that I have sodium chloride, that doesn't matter. What matters is what is it dissolved in. Since it's aqueous, my solvent is water. Okay? Now, where would you get the Kf value? Well, in this problem, it's given to me. But if you did not have it given to you, you would look on a table. And if you look in your notes, you have a little table down at the bottom that has Kf, and we'll see Kb values here in a second. And that's how we would do that calculation then. So let's work this one out. I mean, let's see how this sample problem works. So what is the freezing point of a 3 molal aqueous solution of sodium chloride? The Kf is negative 1.86 degrees Celsius over molality. Okay, so our formula, delta Tf, is equal to I times m times Kf. Okay, this is sodium chloride, right? NaCl. We've done this a bunch of times already in this lesson. How many particles does that form? Right, it breaks up into 2. Okay, so we come over here and I plug 2 in. My molality is given to me. Okay, so 3.0 molal times my Kf value that is also given to me, negative 1.86 degrees Celsius times molal. Now you can already see that the molalities are going to cancel out. And we're going to punch this in our calculator and we're going to get negative 11.16 degrees Celsius. Now here's what's important. This is not the new freezing point. This is the change in the freezing point. So to actually get the real freezing point, you have to add your delta T here, the answer that I have right here, to the actual freezing point. Now, conveniently, what is the actual freezing point of water? Okay, right, it's 0 degrees. So that means that 0 plus negative 11.16 degrees Celsius equals negative 11.16 degrees Celsius. We'll see here when we do boiling in a second that it's not always exactly what that is. And if it wasn't water, if my solvent wasn't water, then my freezing point would not be 0. I would look it up on the same table that's in your notes. So if you had like ethanol or phenol or something like that, you would just look that up in the notes. Okay? So that's freezing point depression. And that, again, okay, so let's go back real quick to our icy road. So the reason that we put salt on the road then is that adding salt to that water is basically going to form a solution there of a given molality. And what that does is it lowers the freezing point so that instead of it freezing at 0 degrees Celsius, so 32 Fahrenheit, it might drop it by 5 to 10 degrees. And so it's not going to freeze at 0 degrees Celsius. It might freeze at negative 10 degrees Celsius, which would be something like negative 25, or not negative 25, but something closer to 0 degrees Fahrenheit. And so therefore it's going to help to, once the freezing point gets lowered, it's going to basically make that frozen solid ice turn into liquid water, and it's going to be able to flow away. Okay, so that was freezing point. Let's jump into boiling point elevation. If you look at this formula, this looks pretty much exactly like the previous one. The only thing that's changed is that it's now boiling point. Okay, so what happens to boiling point? Boiling point is elevated. Okay, elevated means it's raised up. So when you add stuff in there, it's going to make the boiling point go up. Now, why is that the case? Well, remember, boiling point is pretty closely related to vapor pressure. Okay, and so these particles want to be able to get away. All right, they want to go into gas phase. That's what boiling is. But if there's solute particles in the way, blocking them, okay, then they can't escape. Okay, they're stuck there and they can't get out, and so therefore they're not going to boil until you reach a higher temperature. Hence, boiling point elevation. I think I just stuck my finger in the camera, guys. Sorry for that. Be thankful it's not 3D. Okay, so same basic equation. Change in boiling point is equal to the Van Hoff factor times molality times some constant. Okay, and so let's work a quick example of that. Same basic formula. So delta TB is equal to I. Again, we're doing sodium chloride, so my I is 2. I've got a 3 molal solution again. Okay, sorry for the writing again. And then the KB is given to us. And remember, if it's not given to you, you just look it up on the handy-dandy little table that you have there. Okay, so that's what it looks like. Molal cancels out. We plug that into our calculators, and we get 3.06 degrees Celsius. Okay, now, just as we said the last time, this is the change in boiling point. This is not actually the new boiling point. So what's the normal boiling point of water? It's 100 degrees Celsius. And so I'm going to add my change in boiling point to it. And that means that my new boiling point is 103.6 degrees Celsius. So if you add a pretty good amount of salt in your water, it's not going to boil at 100 degrees. It's going to have to go up a little bit higher to get there. Okay, a couple of more quick points we want to roll through. The other important area for colligative properties, and we're not going to go too far into that, but it's something that you may remember from biology called osmotic pressure. Osmotic pressure basically says that, remember that you've got the semi-permeable membrane here, and if you have a solution on one side, the water molecules want to go through that membrane to the side with the solution. Basically, they want to go through here and dilute the solution. When that happens, what was a level solution here, okay, water and sucrose, the water now goes down because it's going in the other side. The difference in those two levels is the osmotic pressure. Okay, and all you really need to know about this is that the greater the concentration, okay, so the more sugar I have over here on the sucrose side, the greater the osmotic pressure is going to be. The other thing of interest to you is that this is actually how they purify most water. They run this in reverse. If you look at your water bottle, very often it says it's purified by reverse osmosis. And what they do in that case is that they take your normal, say, tap water, and they do a semi-permeable membrane, and then they force it through the other side. The particles can't get through the membrane, but the water can, and so it purifies the water for you. All right, one last quick thing. Henry's law says that gases are soluble excuse me, in direct proportion to the pressure right above the liquid. Okay, so what does that mean? So if we look at a soda bottle, okay, right above the liquid, there's this little layer of air there, right? That little layer of air is usually under really high pressure. Quite often it's around 5 atmospheres or so, so 5 times normal pressure, and that particularly is of CO2. Now, what does that do? What that does is that if you look at this bottle, like before you open a bottle of soda, you usually don't see any bubbles, or if you do, it's just a few little tiny bubbles, because they're all dissolved in the solution. Once you open the bottle, though, you lower the pressure, and since Henry's law says that you need the pressure to keep all the gas in solution, as soon as you open the bottle, all of that carbon dioxide that's dissolved can't stay dissolved anymore. There's no pressure above it holding it in, so it starts to fizz out. And that fizzing out actually has a special name. It's called effervescence. I think I so spelled that right. Effervescence. I may have spelled that wrong. Okay? Effervescence is when all those bubbles come out sort of all at once. All right? So, a few definitions there, a couple of easy calculations. We'll walk through some of those in class. Remember that if you're doing the boiling point elevation, freezing point depression, you have to know how many particles it breaks up into, and you got to look on the table and make sure that you're using the right solvent.